the hypothesis that I decided to test for my dissertation was the idea that species trade-offs may drive succession. And the reason I decided to test this trade-off is because it's been shown to hold true across not only plant communities but also protozoan communities as well. So it's been shown that in successional species, there's often a relationship between the colonization ability of those species and their competitive ability, in such a way that early colonizing species are often very poor competitors. Later colonizing species are not as good at colonizing, of course, but they tend to be superior competitors, resource competitors, and therefore they're able to drive out the earlier species and replace them. So the question is whether this actually occurs in metazoan communities or not. As far as I know, this has never previously been tested with a metazoan community. So I decided to test whether container species actually exhibit a colonization-competition trade-off. So in theory, this would be a very straightforward experiment. You just measure the colonization ability of multiple mosquito species, you measure the competitive ability of multiple mosquito species, and you just use regression to determine the rate if there's a relationship between the two. But there's a problem with that, and that has to do with measuring competition. So in our lab, if you've heard talks from people in our lab, the way we normally look at competition between two mosquito species is by running what we call a response surface design experiment. What we do is we set up several different treatments, so individual containers that will either contain only species 1, only species 2 in various densities, or some combination of interspecific combinations of the two species. We then rear those containers under standard conditions, so the larvae are reared until eclosion. Once all the animals have eclosed, we use certain demographic data that we obtain from those containers, such as the proportion of animals that survive to adulthood. And then for each of the species, we can run multiple regression to determine how each of the species are responding in their survival to either their own density or the density of the opposite species. And so you look to see if there's a difference in the shape of those two planes, and you determine, based on those analyses, which of the two species is the superior competitor to the other. Now, this is a very thorough and excellent way to look at competitive ability between two species, but if you try to expand this beyond to test more than two species, you're looking at the recipe for a tenure track student. And I'll just give you a brief example of that. So in order to test two species, in order to get one replicate of treatments, in order to test competition between two species, I need about 10 containers and about 280 larvae. Not so bad. If you're looking at 3 species and you want to test all the possible pairwise combinations of those 3 species, you now need 21 containers and over 600 larvae, getting a little dicey. If you go up to 4 species, you now need 36 containers and over 1,000 larvae for one replicate, mind you, and you have to run multiple replicates in this experiment. And if I decided to test most of my community, as I had hoped to do, I would have needed 700 containers and over 6,000 larvae just to test a single replicate using the response surface design. So fortunately, there is theoretically another method out there, and it relates to resource competition theory, and it's a value that's known as R star. So R star is the amount of resource that any species needs in order to maintain a stable equilibrium population. Imagine that you are looking at the population growth rate of a species in response to an increase in resource amount. So for a species, you might expect the curve to have a shape like this. Wherever that curve intersects 0, wherever there's 0 population growth rate, the amount of resource that the species needs in order to maintain an R of 0 is going to be that species' R star. Now imagine that you have a second species with a slightly different response in growth rate to that resource. That species is going to have a slightly different R star value. And so on if you have a third species. It too is going to have a different response to that resource, and it will have a different R star value. Now, if you can obtain the R star values for multiple species, you can use those values in order to rank them by competitive ability. Why? Because in this case, species 1 is going to be the most competitive species because it has the lowest R star. It's able to maintain its population with a lower amount of that resource than any of the other species in the system. Species 3, on the opposite end, is going to be the worst competitor of these three because it needs a greater amount of resources in order to maintain the same population size. So we set out to see if there was a method that we could use in order to estimate R star for multiple mosquito species. And we also tested to see whether that method was as predictive of competitive ability as the typical response surface design experiments that we did. So to do this, what I did was I took 3 species that we knew a fair amount about, Culex pipiens, Aedes aegypti, and Aedes albopictus mosquitoes, and I reared them in standard intraspecific densities. They were never combined with each other. They were always kept at separate standard densities. Instead, what I manipulated across treatments was the amount of detritus, or the amount of resource that was available to those. I then reared all of those containers to adulthood in the laboratory under standard conditions, and I took certain demographic data like the number of surviving females, the size of those females at eclosion, and the amount of time it took for them to develop. And I plugged that into a handy equation that Livdahl and Sujihara came up with in order to estimate R prime for each of the containers for each of those species. I then took the exponential of R prime in order to get a value called lambda prime, which is the estimated finite rate of increase. The reason I did that is because with lambda prime, you actually use containers where there were no surviving females, whereas if you're working with R prime, you have to throw those containers out. So this way I was able to incorporate more of my data using lambda prime. So what did I do with those values once I obtained them? Well, what you can do, these are theoretical values, by the way, these are not my real data, is you can take those lambda prime values and you can plot them with the amount of detritus that is in each of the containers. Then, for each of the species, you can determine, using nonlinear analysis, the relationship between the change in lambda prime in response to detritus amount. Wherever that line crosses lambda prime equals 1, that's going to be the equivalent of R equals 0. So that's going to be the equivalent of population equilibrium for that species. And the resource amount, the detritus amount, where lambda prime equals 1, is what we're calling R index, which is the equivalent of R star. So because it's the equivalent of R star, a lower R index is indicative of greater competitive ability of the species. So we did that for the 3 mosquito species, and what we found was that Aedes albopictus actually had the lowest R index value at 0.12. Culex pipiens had the highest value at 0.94, and so based on these results, you could rank them by competitive ability. In this case, you expect pipiens to be the worst competitor, Aedes albopictus to be the best competitor, and Aegypti falling somewhere in between. Now, at the same time we did this experiment, we concurrently ran the response surface design experiments that I just explained to you, where we paired the species with each other with both standard intra and interspecific densities, and then we assessed their competitive response to one another. What we found was that Aedes albopictus was significantly affected only by Aedes aegypti, and in fact the main effect came out slightly positive, if anything else. So albopictus wasn't negatively affected by anything. Aedes aegypti was negatively affected by albopictus by itself, but not by Culex pipiens. Culex pipiens, however, was negatively and significantly affected by everything. So what does that tell us? It tells us that Aedes albopictus, under this scenario, would be the best competitor. Culex pipiens is the worst competitor. Aedes aegypti follows somewhere in between. These results from the response surface design studies exactly match these results. Because of this study, I use this as justification to use R index, measure R index in as many container species as I could get, and use that as a measure of competitive ability for those species.